Okay, cool. Hello, everyone. Thank you for joining us for the last session of the RL seminars before the summer break. After that, we'll be gone for like a few months, I think, and we'll probably come back in September. And so for this last presentation, today we have like Nneka Okolo. She's a postdoc. She's currently a postdoc at MIT. And prior to this, she was doing a PhD at Pompeu Fabra University. She was working with Gerge, who's also here, and she was working on reinforcement learning, stochastic optimization, online learning, all the things we like, and towards applying like reinforcement learning for real-world applications. She's particularly interested in like developing error algorithms for large environments. Where like the number of states is typically infinite, but like could be like very much finite, but so large is like intractable. With and she wants to do this in like with like guarantees and super complexity guarantees and so on. And so we are very happy to have her today. So Nneka, thank you for accepting our invitation, and you can go ahead.
Okay, thanks for the introduction, and I'll just share my screen. Can you confirm if you can see it, because I can't see anybody?
Yes, looks great.
Okay, so today I'll be talking about our work on provably efficient offline reinforcement learning via a method we call Feature-Occupancy Gradient Ascent. So this work was done during my PhD at Pompeu Fabra University with advice from Gerge. So in the paper, we are interested in offline reinforcement learning, which is a useful setup when you're talking about risk-sensitive error problems, where such as autonomous driving, where trial and error learning in the true environment is expensive, but logged interaction data from a preferably diverse set of expert actors is readily available. In this setting, and for example, for real-world problems such as autonomous driving, where wrong actions could have really drastic outcomes, we ask the question, can we learn a good strategy from a static data set of interactions? Where by good, we mean a strategy that leads to high cumulative rewards, has good theoretical guarantees, and is, of course, implementable. Guided by these three characteristics, the rest of the presentation is structured as follows. So first of all, I'll formally introduce our problem set and research question. Then I'll talk about our main assumption, our algorithm, results, and analysis. Then I'll conclude. Now, for the problem setup, we focus specifically on our problems, which can be modeled as an infinite horizon discounted MDP, which we denote here by this tuple, where nu zero is the initial state distribution, S is a set of finite, is a finite but really large set of states. A is the finite set of actions, R is our reward vector, P is the transition matrix, and gamma is the discount factor that takes values between 0 and 1. We also assume that the actor can interact with the environment over an infinite number of steps, and that the decision process is Markovian, meaning that in each step, the actor's immediate reward and next state transition depends on only its action in the current state, not on its entire interaction history. Given this setup, by standard notation, we refer to the learner strategy as a policy, which is denoted here by pi, and we measure cumulative reward in terms of the normalized return, which is denoted here by rho pi, which by definition is the normalized expected discounted sum of rewards for following policy pi in the environment from any state sampled according to nu zero. Also, we refer to an optimal policy as pi star, And in order to develop theoretical guarantees, we measure performance in terms of the pseudo-regret of any learning algorithm over T training steps, where the pseudo-regret is denoted by RT pi star and is by definition. So for a learning algorithm which produces a sequence of policies pi 1 to pi t, the pseudo-regret basically measures the average loss of the algorithm in terms of return with respect to pi star. And feel free to ask me any questions in between the talk. So another important concept in...
Yeah, question.
Yeah.
Maybe need to raise hands or something. Pseudo regret. I see that you're going to talk about offline, and I guess the pseudo regret is usually considered when you're learning online. I mean, like you can consider pseudo regret and then talk about that. Or if I take the mixture policy, which at random chooses one of the policies, this is how much simple regret it would have. Is that what you have in mind?
Yes, that's what I have in mind.
Okay. Okay. Yeah. All right. Makes sense.
Okay. So another important concept in offline reinforcement learning is what we call coverage. And to simply illustrate what this means, so we assume that there's just a single expert actor acting in the environment according to a behavior policy, which we denote here by pi b. And this expert actor acts in the environment and generates a data set of n interactions, with each interaction having an initial state, current state, action, reward, and next states, which are sampled according to the true environment dynamics. So given this setup, we know that if pi b only visits a subset of the state space, which is highlighted here in red, or does not sufficiently explore actions preferred by an optimal policy, then we cannot really guarantee that any learner would be able to learn a near optimal policy with just access to this data set of interactions. So, so that's for coverage. And to conclude the round of notations, I just want to note that we can also express the return of a policy, rho pi, in terms of what we call value functions and occupancy measures, which is standard in reinforcement learning. And precisely, we can express rho pi as this dot product of the initial state distribution, and v pi, where v pi here is the state value function, so such that v pi, and is defined such that v pi of s is basically the expected discounted sum of rewards for being in state S, and q pi of SA is the q pi of SA is just the immediate reward plus the normalized expected discounted sum of rewards for following policy pi in the environment. And also we can have a similar expression in terms of occupancy measures. Basically, we can write rho pi as this dot product, where now we have this new notation mu pi, which can be decomposed in terms of a policy and nu pi. This is a nu, not a v. Where nu pi here is just going to be a state occupancy measure. It basically says that, so nu pi of s basically says that you're in a state, either because you started from that state with probability 1 minus gamma, or you arrived at that state from some previous state with probability gamma. Now that concludes our round of notations. Any questions? Everything's clear.
Yeah, everything's
clear. Okay. So given this setup, to formally phrase our research question, so given the setup, we ask, can we develop a provably efficient and near optimal learner for offline reinforcement learning in large discounted MDPs from just a static data set of interactions, where now we refer to a provably efficient and near optimal learner as one that achieves sublinear regret after a number of steps and with a number of data samples that's polynomial in all relevant parameters, but not the number of states. Because this, given the setting, the number of states would be interactively large. Now, this question has been widely explored in the literature under general function approximation, which is a framework for large-scale reinforcement learning. However, most notable methods in this context are either oracle efficient, meaning that their theoretical guarantees do not directly transfer to a much simpler linear function approximation setting, or they rely on stronger coverage assumptions in that in the linear function approximation framework. Now, given this, in view of these limitations, what we decided to do in the paper is to take a step back and consider the most basic and fundamental structure for developing provably efficient methods in reinforcement learning, which is the linear MDP framework. And so under this framework, we basically follow two assumptions, which is that we have access to a feature matrix phi, and that the dynamics model, meaning the reward and the transition function, can be linearly expressed in terms of this feature matrix phi. That means there exists some weights, omega, for the reward and phi for the transition model, such that we can express the reward vector and transition matrix in this form. So one other thing that we assume in the paper is that the feature matrix itself is full column rank, meaning that, and what this permits is that then we can say that, or rather we can be assured that the value function of every policy, the action value function of any policy, is linearly realizable in the feature space with respect to some unique weight vector theta pi. Now, under this linear function approximation framework, we know from previous works that fully efficient learning is indeed possible, at least in the simple case of finite horizon MDPs, under a weaker unidirectional feature coverage condition, which no longer requires us to require coverage in the actual state action space, but only in a lower dimensional feature space. And this idea has also been extended to, or this concept of unidirectional coverage has also been extended to the infinite horizon setting by Gabbianelli et al., but with a worse sample complexity guarantee. And but further still, this sample complexity guarantee has been improved by Hong and Tewari at the cost of a worse coverage constant in the bound. So what is left, or what we feel was left when we came up with this work, was how do we get the best of both worlds? That's the best of these two papers. So basically developing a method that has an improved sample complexity guarantee, similar to what Hong and Terrari provided, but with better data coverage requirements, and of course without this worse coverage constant in the bound.
Yeah, I do have a question. Going back to the slide where you were talking about the linear MDP assumption, I get a little bit confused about this full column rank assumption. Like, do you really need that for concluding that for any policy pi, you will have this linearizability assumption. I would have thought that you don't really need it. I mean, if you don't have full column rank, like some, like there are some unnecessary features, you can reduce the feature space, but who cares?
So yes, maybe we don't exactly need this full column rank assumption. So that would be the most basic assumption for this theta pi vector to be unique, but
Yeah,
there could be simpler.
but uniqueness is maybe not needed. Well, I'm curious about whether this is going to be a requirement for the algorithm, or because it didn't really follow that, like, that you should have this. Okay, maybe we can return to this later.
Yeah, so for the algorithm, no, this is not necessarily needed. We
Okay.
just need
All right.
exist
Hmm.
unique. Yeah, but
Cool.
the algorithm.
Yeah. Okay. Good. Then we can just drop this.
Yeah.
Okay.
So this is what we know so far in the general linear function under the linear function approximation framework. And now what we would like to do is to get the best of both papers, what has been achieved so far. And to achieve this, we developed an algorithm which we call FOGAS, which I hear is also the name of a delicious fish in Hungarian. And the way we achieve this is through the linear programming approach, which if anybody has heard my talks before, that's basically what I've talked about most of my PhD. So basically, but now we'll be focusing on the linear programming formulation for linear discounted NDPs, which was first formulated in the paper of Gabbianelli et al. And so here the primal formulation has, so here we are presented with two LPs where the primal decision variables are mu and lambda, while the dual decision variables are v and theta. And this might be a lot of notations to take in, but the important thing to note is that the optimal solutions of these LPs can indeed yield optimal policies, meaning that if you can exactly solve these LPs and find their optimal solution, then it's possible to extract an optimal policy from either the primal solution or the dual solution if you know the transition. Maybe you don't know transition model in this case since you have theta. But so this is one good thing to note, and I don't have the proof for it here, but I'll be happy to discuss more about it. And another thing to note, which has already been established, is that we can indeed approximately solve the corresponding min-max problem with only order D log A computations and offline samples. So basically not requiring a number of samples that depends on the number of states at all. And so actually the min-max game in question is the following, where now we have a max and a min over the Lagrangian, which is defined here. But one key question is, like following the work of Gabbianelli et al., is how to estimate the gradient of the objective, especially given that there's this unknown quantity psi, which corresponds to the weights of the transition model. So how do we estimate gradients of this objective with fewer samples than what was done in their paper? And so what I would like to mention is that moving forward, I would assume that the weights corresponding to the reward vector is known or can be estimated, but this work should also be easily extended to the case where this is also unknown with the methods that I'll present now. So given this question, well, this has been partly answered in Hong and Tewari. thanks to this least squares inspired adjustment to the original LP, which follows two steps. So first, they fit an estimator psi hat of the true transition model weight psi using samples from the dataset. So this is just a regularized least squares estimator of the true transition model weight psi. And they instead propose to solve this approximate version of the original min-max game, where now the objective depends on the estimator, is defined with respect to the estimator psi hat and not psi. So, well, that is nice. There's still a question of how to solve this without the without a worst coverage constant in the sample complexity bound. And to achieve, first of all, we utilize a reparameterization trick. I think I heard a ding, so maybe there's a question.
That was me. Yeah. Sorry to interrupt, but I just realized that I don't really know what you meant a few slides back. I'm so slow. When you said that you can solve this pair of LPs in d log a time. So you mean that's an iteration cost for an iterative method? Because I'm like, even accessing the LP requires enumerating all the states if you literally solve it. So what is being meant there?
Oh, what I mean is that you can definitely you can approximately obtain
So you have
and
some
it
wrappers that give you some gradient information or give you some, I don't know, some information about the LP somehow. That's
so you have a way to estimate the gradients of the yeah.
or maybe you meant that like if I have access to some elementary expectation operations that involve the huge current state space, then you can have an exact solver or something, or like approximate solver that whose runtime is d log a. By the way, the d dependence seems to be very low for any kind of claim that that is for solving LPs. It's usually d to the 12 or something. But I guess it kind of suggests that you're talking about iteration cost for an iterative method like ellipsoidal method or whatnot.
So sorry for the confusion, but I'm not talking about exactly solving the LP as it is.
Right.
Trying to summarize the result from this paper to show that
A few slides back, there was a claim about the d log a complexity. And I said that we're going to build on that. That's why I'm asking this question, by the way. There was no d log a. I think maybe I'm dreaming this, but when you had the two LPs next to each other, the primal and the dual, where is it?
Here.
Then on that slide, in the bottom, whoa, okay, there was a d log a computations and offline samples. Okay. Okay, so I see. So that was specific to this offline setting where this is an iteration cost, I assume, because the sample size will matter and whatnot.
Yeah.
Also,
yes, there's a 1 over epsilon dependence as well, which is not shown here. There's a 1 over epsilon to the 4, something like that.
Yeah, and the d dependence is still pretty low, so that's for LP solving. It's
I need to confirm, but maybe at most d squared.
For iteration cost, I would believe this is true, but usually when you're solving LPs, you have to do a bunch of other things like projecting and whatnot, and those can be really costly. But maybe somehow that doesn't apply here.
So this is not, I'll just admit that this is not I should have written poly d log a. So this is not the true complexity. But I was just trying to summarize what was done in this paper to show that, okay.
Yeah. No, yeah, I understand. And I understand it now better a little bit, but I guess like coming to the new thing, like we will clarify all this. Like, okay, good. Yeah, sorry.
Yeah, so in summary, this is not properly stated, but basically you can approximately solve this LP with some further reductions with poly D log A computations and samples. And this is the complexity for an iterative method.
What method?
For an iterative method.
Iterative method.
Yeah.
Okay. All right.
Okay. So I've talked about the LPs, the LP inspired by Gabbianelli et al., and I've talked about the min-max game, which we would be interested in, and the main question, which is how to handle not knowing psi. And I've talked about this approximate formulation that now depends on psi hat instead of psi. And now going forward, so then the idea would be to try to approximately solve that min-max problem. But before getting to that, we know that with a reparametrization trick to handle the high dimensional vectors mu and v, so basically by reparametrizing them in this exact form so that some of the terms in the objective cancel out, then we arrive at this further reduced min-max problem that only depends on d-dimensional parameters lambda and theta and pi, which would be nice because eventually it's we'll define it as a compactly represented policy that just depends on theta. Okay, so yeah, we want to solve this reduced approximate min-max game instead.
Oh, wait, what's the role of pi here?
The role of pi is just here I find as some arbitrary policy.
And okay, so no matter what the policy is, like the solution of this gives you a solution to whatever we had before that didn't have any policies.
So we would iteratively update pi in terms of data. So eventually, yes, it's possible to get that kind of guarantee.
Okay, so there will be an outer loop that somehow changes pi. Okay.
Yes, something like that.
Oh, okay. So there's no claim that like for some pi, maybe for some optimum pi or whatnot, like the solution to this game would give you a solution to the original problem, but okay, like we don't know that pi, so we're gonna also iterate pi.
Actually, for an optimal pi, if this was psi instead of psi hat, the solution corresponding programs would give you a solution to with like the optimal feature occupancy feature station, and theta would, I think, be also the weight vector corresponding to an optimal action value function.
Yeah. Okay. Sounds good. Okay.
Okay. So our method, Feature-Occupancy Gradient Ascent, basically attempts to approximately solve the min-max game, which I just presented, in 2 steps. So over t iterations, what we do is that, first of all, what's important to note is that for a specific schedule, precisely if we define lambda t earlier on, then it's possible to exactly solve the mean problem. Well, this is no easy. It's possible to exactly solve the mean problem and obtain theta t greedily. and then solve the max problem iteratively via an unconstrained optimization scheme. So basically, FOGAS is just this two-step approach that exactly solves the mean problem in each round and approximately solves the max problem using using a mirror descent style approach. Any questions? And now the policy is just the softmax policy defined with respect to the theta iterate.
Yeah, it's a bit surprising how this works, right? Like generally, if you need to solve a min-max game, this wouldn't work. I guess like it's a very nicely conditioned game. Like you
Yeah.
have, can you go back to the like objective function that we have? Okay. So everything is kind of just bilinear or linear. Like no, you are adding regularization like for the lambda part, right?
Yes.
So somehow that makes it like a gradient ascent algorithm essentially for at least one of the parameters, and then the other is best response. So okay, so we know that would work in general. So that's fine. Okay, I understand. Yeah, thank you.
Okay. So sorry if my description is not clear enough.
I mean, like, yeah, it's clear. I'm just, you know, like I keep being puzzled about little things. Yeah, but so maybe you can just like confirm that my understanding is correct, that the update for lambda t is basically an iterative gradient descent type of update, which is like try to stay close to the previous parameter. And then also optimize the objective a little bit, the linearized version of the objective, and that's it. So that would be kind of gradient descent. And there is this lambda, capital lambda n. I don't know whether that has been introduced. That puts the like used in the norms. What is that?
Yes, I should have. So lambda n is just.
It was on this slide. Yes, I see. Okay, so feature covariance regularized with beta. Yeah. Okay. Yeah. Can we go to the other slide? It's really interesting. Yeah. Okay. So you could see that those are kind of like uncertainty terms, if you wish. It's like you don't like the lambda for which you don't really have any much data for those components. You want to have zeros or something. So that's this penalty with the row, right? Maybe.
Yeah, with row, yeah.
Yeah. Got it.
Yes, so this is just basically more or less like this part is just basically more or less the mirror descent style update. And then this
is also gradient descent if you use this Euclid and Bregman divergences.
Yeah.
By the way, Asaf is trying to ask a question. I see it.
Yeah, hi. Maybe if you're gonna get to it, then skip my question. But like, how do you choose the update rule for pi? Like, is it directly derived, or do you just need some kind of regret minimization algorithm like mirror descent so you get this?
Why do you choose the softmax policy?
Yeah, because eventually to control the regret of pi.
Right. So we can use this.
So just you need to run like a regret minimization over your empirical loss, essentially.
Yes. Yeah.
Thanks.
I also had a question about the computation of theta t, whether it has some nice interpretation.
Okay, so the computation of theta, like this expression.
I don't even know what this d of theta is. Like, what is that?
Okay. So because we are doing best response, but within this convex set, I don't know if you can see it, BD.
Yeah. Yeah, so
So
that's the radius.
just the size, yeah, just the radius of the.
Okay, so that's the real number. Okay.
Yeah, so basically 1/1 minus gamma.
Okay, so we basically okay. So somehow this is the relevant part of the objective, and then you just take the vector, that gives you the direction and normalize it, and that's your next. Wow.
That's theta t.
That doesn't look like any value function training business at all. Yes.
But
Does it?
yeah, definitely like any value function update. But I think what Gergo pointed out at some point is that if you squint at this lambda updates a bit, then like if you write it exactly as a max over this function plus the regularization term, then and if you if you optimize this theta t exactly like this, then you would see that basically what lambda is trying to do is trying to reduce what looks like a Bellman residual error.
I see. So rather than, we already estimated the Bellman residual error, it's the dimensions here. What is this phi transpose mu hat theta? Oh, I guess mu hat theta is.
Oh, mu hat theta is
It's expanded in terms of the data.
Yeah, it's an estimate of mu pi t lambda t. And because this is a sparse matrix and we'll eventually assume that the initial fixed, then it has a direct
I
expression.
see. Yeah, I wanted to ask whether this new zero needs to be sparse or something. Seems it should better be sparse. You sample from it, maybe that would also be sufficient.
Basically, to avoid a computation depends on the number of states. This is fixed at some state matrix.
Yeah, got it. Okay. Yeah, very interesting.
So kind of the interpretation that I was pushing for, I don't think I ever managed to do that successfully, was that, well, basically what happens here is that since theta is playing best response to lambda and pi, you can really think of this as just gradient descent or gradient ascent on the primal function. So you have the Lagrangian, right? And then you take the max of that with respect to theta. The dual variables, I guess. Oh yeah, the min. And then just do like preconditioned gradient descent on that.
Yeah, got it. Okay.
Yeah, but there is this pi as well that sort of confuses things or makes things like a little bit more complicated. But somehow magically it all works out.
Yep.
Right. Yeah. Sorry for the interruption. Yeah.
So, and to note here is that, so I've talked about the algorithm, but in contrast to the work of Hong and Tewari, one key thing to note here is that this unconstrained optimization scheme, which was done in an earlier work, actually allows us to do unprojected, basically gradient descent with added regularization without projections on one hand. And on the other hand, it allows us get an instance dependent bound which is nice because eventually the coverage parameter that the desired coverage parameter that we would prefer to be in the bound basically comes out from that. And in contrast to Hong and Tewari, then we didn't need to do projections and we didn't need to define a compact set in advance and do other stuff which led to added complications in their algorithm.
You still
Question?
have one projection.
Sorry?
You still have one projection, one compact set lurking around. Did you have it?
For theta,
Yeah.
you mean? Yes, yes. But
That's
for
what my-
lambda, for theta, it's okay because you can
Really?
define. I mean, this set is easily defined, and d theta has an expression which is acceptable in the bound. For lambda, it's more like it's just best to have an
Isn't
unconstrained
your bound is going to be of the form of like,
update.
if my true parameter lies within this set, then nice things are happening. And you can't say anything about when it doesn't.
Yes, so basically, not having to do projections allows us to not have to go
But
through. But for
you're still
theta,
doing a projection with respect to theta.
yes.
You eliminated one of the projections, but not both.
Yeah, not both. Because
Okay.
this projection is easier to execute, and also d theta has a nice expression which is okay in the bound. And of course, the compact set is defined based on the idea that, okay, we have a reference point, which in this case would be theta pi t for any policy pi t, and we want that point to be in this set.
Yeah, but maybe theta star, or like for the optimal parameter vector, its norm is much bigger than that. So how do you know that your d theta is big enough? Wouldn't you need to adapt to that?
Because we make it, basically we make it big enough. So we set d theta to be of the order square root d over 1 minus gamma.
And why is that sufficiently big? I scale down the features, my theta star norm goes up.
If you scale down the features.
Yeah.
It's
They're
sufficient.
inversely related.
The action value function of every policy, the norm of that is at most 1 over 1 minus gamma.
How do you know? That's based on the assumption, some assumption that some people made at some point, but I don't think that it's something you can know.
Okay.
Yeah, so that's just from like the Jean Yang Wang and Jordan paper.
Yeah.
Right. That
But then
everybody
make up this assumption, and then everyone uses it. Yeah. Okay.
Yeah, I mean, I think that this can be eliminated by replacing this hard projection to a ball to just like minimizing, let's say, like a regularized objective.
Something like that would be nice. Yeah.
So if you don't regularize with the convex indicator function, but with the squared norm, I think it should be fine.
But wouldn't the parameter for that regularizer need to depend on unknown quantities, or?
Yeah, if you want to put it under the square root or something, if you want to use like the right scaling, but you would get a guarantee.
Kind of the
Maybe.
hard part of this is that, like, if you only have offline data, then like you cannot really verify anything, right? Like about the performance of your policy. So it's like tuning these hyperparameters might just be, not possible.
Yeah. So I mean, I really think that like getting rid of the projections for lambda is the big deal, because the norm of lambda star would need to depend on the coverage of the optimal policy, and there's absolutely no way of knowing that. So getting rid of that assumption, I think that is the main big deal. I think it can be done for theta as well if you really want, but I think that the paper would get 10 pages longer and minimal gains.
I would be interested in that paper, but like maybe some future paper. I tried to get rid of this assumption in other settings, and it's not easy. Okay, great. Thank you.
Thank you too. And so that's the algorithm. And now our main result is the following. So let's redefine the C5 as a coverage parameter. And basically what this guarantee is saying is that if the initial state distribution is fixed at some state S0, and the data set covers well a single direction in the feature space that's characterized by lambda pi star, which is just the feature expectation under the occupancy measure corresponding to an optimal policy mu pi star, then we can guarantee this bound on the pseudo regret after a number of steps and a number of samples that depends on some parameters, but not on the number of states. And we have this guarantee with probability at least 1 minus delta.
What is capital R here?
So R here is a bound on the normal of the feature vectors.
Okay, d theta.
Yeah.
Wow.
Yeah. R is not d theta, it's just normal, the two norm of the feature vectors.
Oh, the feature vector norm. Okay, okay. Oh, okay. So where's d theta from this bound, in this bound?
So d theta, I think I showed it's
Hiding in a big O?
minus gamma. See, it's of the other square root of d, 1 minus gamma. So it's
Yeah, usually what happens if you have a gradient algorithm, then it needs to adapt to the norm of the parameter that you're estimating, even supervised learning. So the cost usually depends on how big that norm is. So either it should be in a cost or it should be in a suboptimality somewhere. You cannot really hide it in, or maybe because of the assumption you have this d theta can be chosen to be 1 or something. Yeah. Okay. That's how it works. Or square root d, like an extra square root d is coming in because of that or something. Yeah. Okay. Sorry. Yeah. Makes sense.
And so this is the guarantee that we get, but I'll just note that while we assume that the initial states distribution is fixed, it's possible to extend this guarantee to when you have nu zero to be stochastic using some virtual algorithm which has been developed similar to what has been developed in a paper by Chaba and Yin and some other students. Okay, so this is the result that we have. And just to put things into perspective, so here I have the algorithms by Gavianelli et al. And Hong and Tewari. And here lambda, not lambda n, is pi b is some behavior policy. And lambda n is the feature covariance matrix under this, under the occupancy measure induced by this behavior policy. And what has been guaranteed in the past in previous works is that you can, in the specific setting of linear discounted MDPs, you can get an other epsilon to the power minus 4 sample complexity guarantee under this feature coverage condition where C can take values between 1/2 and 1. So it's much smaller if C is equal to 1/2. Also, you can get a better sample complexity with Hong and Tewari method with this condition. Of course, because you consider,
Can I ask a question?
yes, sure.
Yeah, it's about the data generation. Is this some IID model of data generation?
So in general, that's the assumption, but in our case, we don't specifically need the IID model.
I would be really surprised because if you have a single sample pass in a Markov chain very slowly mixing, then you should see the mixing constant, mixing time somehow in a bound. Maybe it's hiding in the feature matrix concentration thing, but is it really true?
You mean in the case of R bound, like you,
Yeah. Your results. It was not clear to me what is the assumption being made about the data. Is it a single trajectory? Like
no,
you have some probabilistic statements, so you have some, random data, and the correlations in the data are totally going to matter, I would think. So I'm wondering what was really the assumption there.
so the data generation assumption we make is similar to the compliance assumption that's made in the work of Jean et al. And in the paper is pessimism provably efficient for offline RL. So
Which is
basically,
what?
the assumption is that the data according to true environment dynamics, but we do not need like IID assumptions.
Wait, can I have a single trajectory then?
Yes, absolutely. You can have a single
Okay.
trajectory. This can be like a bunch of different trajectories, like arbitrary data. This works for
So what type
whatever.
of concentration result are you using for proving this result with a single trajectory, let's say? Yeah.
Well, it's a data-dependent guarantee. So the right-hand side depends on this lambda.
Right, but you still have this log 1 over data. So some
Normalized.
concentration result is being used. So it's some martingale stuff only that you can have for free in Markov chains. I guess it must be the case. Yeah.
Yeah, it's like a standard self-normalized tail inequality. That
Yeah.
I
lambda.
see.
Yes, in this paper.
Yeah. Okay. Yeah. Okay. Okay. So if you have a bad trajectory, then this constant blows up and that's it. This, yeah.
Yeah.
Pretty cool. Yeah.
So if you have a bad trajectory, yes, it blows up, because remember that the coverage parameter also depends on pi star.
Yeah.
So,
Oh, related, like this result, of course, doesn't depend on pi star. Like you can compete with any policy of your choice.
well, yes, any policy that you're interested in. But this regret is going to blow up for that policy if
Yeah. If it's not covered by the data, but
with respect to that particular policy.
right. And then the dependency in the sample would only impact this constant, and that's isolated to that. If someone wanted to analyze that, they could do it, but then you would need to bring in mixing time or something. But if you don't do that, then you don't need it. Got it. And this was true for the other papers as well. Somehow they are using a generous data assumption like you.
What theta assumption?
No, data.
Oh, data
Like,
assumption. So required the behavior policy to be fixed, and is they required it to be known specifically for Hungary and one case for Gab.
yeah.
And they also require the IID assumption.
Yeah. So there are pros and cons of this data-dependent term. Right? So the non-data dependent term could be actually stronger when the data dependent term is actually big, but like on average it's small, but like on this trajectory it's big. And yeah, so or put it another way, if I ask you that so to put things on equal footage, assume that you have a single behavior policy generating the data. Can you get a bound that depends on the expected coverage of the features and without blowing up this term, right? Maybe you can.
Okay.
Yeah.
Yes, you.
So that would be a concentration question of like, does this quantity, empirical quantity, concentrate around its mean quick enough? And what happens with the inverse is there is some minimum eigenvalue business that it's a little bit scary, but yeah, I guess it can be done. And the extra terms that would come out from that analysis would be lower order, because it would be like at least 1/√10, or like at most 1/√10 difference between the expected value and the empirical value, and then the extra error term that you have is 1/n, so it's fine.
I tried to do that. This is but because of this inverse, it does make things
Yeah.
a bit more tricky. But yes,
Yeah.
there could be a scenario where this with c equal to 1/2 can be better than this.
Yeah. I would expect some matrix consultation will give you this result, but maybe.
Yeah, right. Yeah, like the previous methods did not really need that because they were stochastic optimization star methods. So not like proving the bound for your data realization and then proving concentration, but like more directly going for the population error.
Right. But maybe you could change their analysis. And then I was actually particularly wondering whether if you try to do that, whether the -2 would be reused. Probably not to -1 in the previous work, because it's, yeah, that's probably would be still there in a data-dependent analysis. I'm just guessing.
Can be reduced to -1 in this case with c equal to 1/2.
Right.
But in that case, they had, like, if you look at the sample
Yeah,
complexities,
kind of a slow algorithm.
yeah, but maybe it could be possible to get like this sample complexity guarantee with -1 here.
Okay. All right.
So basically, we can get an order epsilon to the power -2 sample complexity bound without needing to commit to a single behavior policy pi b, or assuming knowledge of this data generating policy. And in some settings, we have a better coverage constant in the bound. And what I wanted to say why this is better is because if you consider the tabular setting and you assume that the data set exactly aligns with the optimal policy, then, well, if this were not the empirical feature covariance matrix, then this could basically reduce to 1, but this term would be of the other SA. So how do we get this guarantee? Now I'd like to walk you through the proof sketch. So to prove the result we've seen earlier, what we do in the paper is that we look at this term, which we call a dynamic duality gap, which takes inspiration from the idea of duality gaps in linear programming. and is dynamic because the comparators here, because some of the comparators are allowed to change with time. So here we define the dynamic duality gap to somewhat mean the difference between the error of the iterates with respect to this function f, where now f is something similar to f bar, f hat, which we've seen before, but now doesn't depend on, is not defined with respect to the transition model, to the transition model weights estimator psi hat, but is now defined with respect to psi. And what the whole summary of this proof sketch is that we can, for a specific choice of these comparators, lambda star, pi star, and theta star t, we can relate the gap to the pseudo-regret, which is the term we're interested in controlling. And on the other hand, we can also relate the gap to the online learning loss of each player in the Fogas algorithm, plus an additional least squares estimation error to account for the fact that we are not using the true transition model weights, but the estimator psi hat. And so for the first part, relating the gap to the pseudo-regret, what's useful to note here is that under the linear MDP assumption, which we made earlier, basically that the transition model weights can be linearly expressed in terms of the feature map phi, and same also for the action value function of any policy, then we can indeed show that the parameterized vectors mu and v, which were parameterized earlier on to avoid having to optimize over them. So these parameterized vectors mu and v correspond to a valid occupancy measure and a valid value function v pi. And this is true because, so by definition, this is how I defined the parameterized vector. And now because it depends on the true transition model weight psi, and lambda pi is just a feature expectation under mu pi, then you can basically substitute this term here and show that this is just going to be the state occupancy measure of policy pi, and so mu pi lambda pi is just the state action occupancy measure mu pi. On the other hand, just by noting that there exists that theta pi is the weight vector corresponding to the action value function q pi, then you can rewrite this expression. Then this expression is just the value function of policy, is just v pi at state s. Now, using these two ideas and taking into account the definition of the duality gap, we can indeed show that the first term in the gap term, which is this f lambda star pi star theta t, when we substitute these specific comparators given here, so for lambda star, we choose lambda star as lambda pi star. We choose pi star as an optimal policy or any arbitrary comparator policy. And we choose theta star t as theta pi t. So basically the weight vector corresponding to the action value function of the policy pi t. Then using this two concepts, these ideas that were developed earlier, we can show that we can just write out this function as this, and because of what's because mu pi lambda pi is just a valid occupancy measure, this second term goes away, and what we are left with is the return of pi star. And on the other hand, by choosing theta star t as theta pi t, we can show that, and using the fact that the parameterized value function at pi t, if we choose the pi's and the thetas appropriately, it's just v pi t, then this second term also cancels out, and what we are left with is just the return of policy pi t. So with that, we can easily, and putting these two terms in the bound, in the definition of the duality gap, we can easily resolve that this term is just the pseudo regret of our learning algorithm. So that's on one hand. On the other hand, we can also relate the gap to the online learning loss. And this is easy to show by just recalling the definition of the duality gap and rearranging terms so that you get so that each of these loss terms have this specific expressions. Precisely, LT lambda star is just the loss of lambda t with respect to this term, this other term in the inner product, which is just the gradient, with respect to lambda, which was used in updating the lambda iterates. And basically what we have here is just the loss terms for lambda, pi star, and theta star. And the last thing to note is that after writing out things in this way, and to answer the question that was brought up earlier on, so pi t, again, defined as a softmax policy, was convenient because then we can control this term, which is similar to the loss of pi t with respect to pi star times some gradient term, which can correspond to some mirror descent update rule. We can easily control these two terms using the mirror descent analysis. And because we update theta t greedily, this term is just upper bounded by 0. And the last term, which corresponds to the least squares estimation error of psi hat, can be controlled via standard concentration argument. Any questions so far?
All good. How about questions later?
Okay.
One more.
Okay, so putting everything together, basically, and writing things in a nice way just gives us the desired bound that we had in our guarantee. And to conclude, so basically, so far, I should have recalled that slide, but okay, so far we have developed a method for fully efficient offline reinforcement learning in linear MDPs, but there are some open questions which would be interesting for future work, which would be, for example, so the improvement we saw earlier on was only with respect to the sample complexity guarantees. There's still a question if we can get a time complexity guarantee that's of the order epsilon to the power -2 under similar conditions, and if we can go beyond the linear MDP assumption. And this is an interesting question because the work that I talked about, the work of Zanetti et al., so they have shown that you can get a fully efficient method for under this weaker unidirectional coverage condition in the setting of Bellman completes. And so, and we know that the linear MDP assumption is of course weaker than that. So a good question would be if in the infinite horizon setting we can also get similar guarantees as that of Zanetti et al. And I think a more recent paper by Nneka Okolo as well. So these are the two interesting future directions, and thank you for being all. That's all presentation.
Yay.
Very cool. Yeah.
I have a technical question if you still have some patience to conclude.
Yeah.
sort of goes back to this projection about theta.
Okay.
This is like generally in linear MDPs, it's kind of a pain that is dealt with when you're estimating the value that you, I don't know, sometimes like if you're doing policy optimization, then sometimes it's an issue to sort of project theta. Well, but projecting it would be fine actually, but like normally I don't know how to do this, for example, without losing a sense of optimism. So like, do you have some intuition why this is okay here? Because like normally, if I don't want to do like the usual clipping of the value or these kind of indicator tricks that we've been doing in recent works, then I was thinking that, yeah, well, sort of projecting theta would be the sensible choice. But yeah, like at least in online algorithms, I'm curious how you can do this and maintain optimism.
Yeah, I understood you were talking about online algorithms. Yeah, because that's a big question that keeps coming up that I've tried to explore a bit before, and I'm still not sure how to do it correctly in the online setting where you have the Q function plus some additional optimism term. So I'm still not sure because the problem there is that the additional term, which often comes in terms of the norm of the, I think, a weighted norm of the feature vectors, that's the bonus term. It's not necessarily bounded, so you can't know in advance like how big the set is going to be. And even if you know, you wouldn't really want that kind of parameter in your bound. So it's still an interesting question how to, if projections can help in the online learning setting.
Yeah. Okay.
Yeah,
maybe
we try to think about this. We try to think about this a lot with Nneka, like how to do this, like how to combine this algorithm with like an expiration bonus and get something online. But somehow this kind of primordial approach, like after all these years working on this with Nneka, somehow I feel that these primordial approaches, especially with these Lambda updates, it somehow introduces some kind of inherent pessimism into the method. So if you like work out the regret bound for the Lambda player, that's gonna give like the exact term that you would expect from like a pessimistic algorithm, like this coverage term. And basically, in order to kick that, you would need to like introduce some additional expiration bonuses somewhere else in this function f. And then every way we tried to do that, somehow something always kept going wrong, and we didn't know how to address that. And I'm still thinking about this, but it's very hard. Yeah. Somehow this approach feels like very natural for the offline setting, but for the online one, still not sure this can work.
I actually have a related question, because like it's really puzzling, because you shouldn't be getting this single policy concentrability bounds for an algorithm that doesn't induce his pessimism, right? So to maybe one case that can be thought about explicitly is, but it's kind of not covered at the moment with the analysis because of a simplifying assumption, is what happens in a bandit. Because in a bandit, we would know that, okay, like this is how pessimism looks like. We also know that if you just estimate the rewards and you're acting greedily, it's not going to fly. So this algorithm must be doing something. I would think that maybe what it's doing is that like there is some non-negativity of the rewards. Your parameter estimate starts at 0 or something. Maybe something like this is, and then you apply gradient descent. Well, it would need to assume that the feature vectors are non-zero. But like, okay, so if you would do all of that and then you're estimating this gradient descent, then you would be slowly growing the weight towards where it should be. And you take an average of the policies with respect to all the weights that you have seen in gradient descent, I would understand. Okay, some pessimism applied, but you don't have the feature vector positivity, blah, blah, blah. It's like, why? How is this happening? Like, how does the algorithm actually knows anything about pessimism? And in a bandit, it needs to know about pessimism. Like we know that estimate acting leader is not going to get this bound.
Yeah, it's really based on different principles, I would say. But so I guess like this lambda parameter, this can really be thought of as like feature occupancies or like expected feature vectors. And the regularization that is being used on the lambdas, as you see, so that has a bias towards lambdas that are well covered, right? Because you're penalizing directions. So you penalize, you get a penalty for moving in a direction that really deviates.
Okay, so the algorithm has this baked-in notion of like avoid uncertainty, and subject to that, maximize reward. No, I'm with you. Like this can work. Yeah, absolutely.
Right. So it doesn't come in as an explicit penalty that you add on top of the reward or the value function estimates or anything like that. It sort of like directly biases these lambda vectors towards things that remain close to the.
No, I can totally see this. Like, and I think we could trace it back in bandits, like you're gradually changing hypothesis, and then you look at like how uncertain you're about evaluating any given policy given the features you have, and you just like say, I don't like those that are uncertain, right? Like penalizing the parameters of those somehow.
Right.
Yeah, got it.
Yeah, and I guess
it's also absolutely crucial for this.
Yeah. And you see that this is pretty much why this idea doesn't work for optimistic exploration, right? Because in optimistic exploration, you would want to go in the directions with high uncertainty, but that would be like a convex maximization problem, right?
Yeah.
And that's not something that's very compatible with this mirror style approach.
Such a sneaky thing.
Yeah. Thanks, that explained a lot as well.
Thank you.
Okay, so that just answered my question.
Okay, so how do you feel if I stop the recording now and you take the other questions offline?
Yeah.
Okay, cool.
And then you.
Yeah.